Two 15,000 kilogram shipping containers are separated by 10 meters, and this is measured center to center. Determine the force of gravity between them. All right, this is an example of Newton's universal gravity law because we're not looking for the force of gravity acting on each individual container as a result of the Earth's pull. We're talking about the force of gravity of traction between the two objects. So the first object has a mass of 15,000 kilograms, and same with the second. The separation distance between them is 10.0 meters. Notice the question is implying three significant figures. So we're looking for the force of gravity acting between the two objects. And since we're dealing with universal gravity, Fg is equal to G m1 m2 over r squared. So again, starting with the equation and substituting our values in. And if you recall from the video earlier, I did have a silly way of remembering what the value for G is. And that's what I call the pizza constant because it's 6.67 times 10 to the negative 11. Hey. 15,000 kilograms for each and a separation distance of 10 meters. So we get a force of gravity of 1.50 times 10 to the negative 4 newtons. So even with objects as large as shipping containers, 15 metric tons each, the force of gravitation between them is shockingly small. Next, sample problem 17. The mass of the Earth is equal to 5.9721986 times 10 to the 24 kilograms, and the radius of the Earth is 6.371009 times 10 to the 6. And I realize now that in my previous question, I misremembered this. I put that as an 8 when in fact it's actually a 9. So given mass Earth is 5.972 1986 times 10 to the 24 kilos. Radius of the Earth is equal to 6.371009 times 10 to the 6 meters. And let's see what other information we're working with. So let's take a look at parts A through D to see if there's any other information. So for part A, there's no new numbers that we're dealing with. For part B, we're asked to find the acceleration due to gravity at an altitude of 400 kilometers. So that means for part B, we have an altitude, or capital A, of 400 kilometers. That is not the appropriate unit, however. We have to convert from kilometers to meters, which means we have to multiply by 1,000, which works out to 4.000, 4 sig figs, times 10 to the 5 meters. For part C, we're asked to find the acceleration due to gravity again, but at the height of communication satellites, which is approximately 37,000 kilometers. Yeah, and you read that correctly. Communication satellites are located 37,000 kilometers above the equator. To give you some context, the circumference of the planet at the equator is approximately 40,000 kilometers. So satellites, communication satellites, are as high as the Earth is round, which is a pretty remarkable number when you think about it. Also explains why you lose satellite signal during rainstorms. And again, this number has to be converted into meters, so we have to multiply by 1,000. And in scientific notation, that gives us, let's assume 4 sig figs, 3.700 times 10 to the 7. Now, I want to show you a quick way that I actually can convert this into meters and into scientific notation. I know the decimal place has to go here. So that's 1, 2, 3, 4 placeholders that it has to move over. Plus, when you multiply by 1,000, that's another 3 placeholders. So 4 placeholders plus 3 placeholders is a total of 7 placeholders. And that's how I can quickly get that number. And finally, for part C, we're looking for the force of gravity acting on a 5,630 kilogram satellite. So I am going to represent that as MS, subscript S, of course. And I'm using a little m because it is a significantly smaller mass than the mass of the Earth. All right, so here are the formulas we're working with. Fg is equal to big G, and I'm going to use the big M, little m notation. You can also use the M1, M2 notation. It's the same thing, but I like the big M, little m because big M represents the mass of the Earth, little m represents the mass of the satellite. Then we can also use this formula for little g, which is big G, big M over r squared. And that's all we need for this particular question. So let's see what we're asked to find. Part A, we're looking for the acceleration due to gravity on Earth. Part B, we're looking for little g at 400 kilometers above. Part C, we're looking for little g at 37,000 kilometers above. And part D, we're looking for the force of gravity at the same altitude as before. So for part A, we're going to find little g. Little g is equal to big G, big M over r squared, 6.67 times 10 to the negative 11. The big M is the mass of the Earth, which is 5.972 1986 times 10 to the 24, all over the radius of the Earth, which is 6.371,009 times 10 to the 6 meters. Make sure we square that. And that works out to 9.814 meters per second squared. Now, part B, we have to find the acceleration due to gravity at an altitude of 400 kilometers above. So using the same formula, however, we have to modify it slightly. So big G, big M over bracket, the radius of the Earth plus the altitude all squared. And the key thing is, don't forget your brackets. So 6.67 times 10 to the negative 11 times the mass of the Earth, which is 5.9721986 times 10 to the 24, divided by bracket, the radius of the Earth, which is 6.371009 times 10 to the 6, plus the altitude, which is 4 times 10 to the 5 meters, which equals 8.689 meters per second squared. Part C, doing the same thing again. G is equal to big G, big M over R squared, which is equal to big G, big M over the radius of the Earth plus the altitude squared. Don't forget your brackets, which is equal to 6.67 times 10 to the negative 11 times 5.9721986 times 10 to the 24 kilograms divided by the radius of the Earth plus this time the altitude of the satellite, which is 3.7 times 10 to the 7 meters all squared, which gives us a value of 0.2118 meters per second squared, which is a very small value. And there's a good reason for that. This is what is called a geosynchronous orbit. That implies that the satellite is rotating or orbiting the Earth at the exact same period as the Earth's rotation. And what I mean by period is the amount of time it takes the Earth to rotate once, which we know to be approximately 24 hours. It's actually not exactly that number. That's why we have leap years and leap seconds and all that business, but approximately 24 hours. So the satellite has to match that period of rotation. That way that the satellite relative to the surface of the Earth appears to be in the same point in the sky at all times. It really is turning with the Earth, but for observers on the Earth, it appears that it's stationary above the ground, which is an important aspect of setting up these orbits because satellite dishes, especially for communication, they are usually set in a fixed position. It would be technically too difficult to have the satellites the satellite dishes having to track the satellites. So we set it up so that the satellites do match the rotation of the Earth. Finally, part D, looking for the force of gravity of our satellite up at that altitude. So FG is equal to big G, big M, little m over R plus our altitude squared. So our pizza constant times the mass of the Earth times the mass of the satellite divided by the radius of the Earth plus the altitude of our satellite, all squared. Again, do not forget the brackets. So we get a force of gravity of 1,192 newtons. And finally, sample problem 18. Two very large asteroids are floating near each other in deep space. The asteroid on the left has a mass of 5 times 10 to the 5 kilograms, and the asteroid on the right has a mass of 1 times 10 to the 5 kilograms. If the asteroids are located 100 meters apart, measured center to center, find A, the net force acting on a third 10 kilogram object if it's located to the left of the first asteroid, B, the net force acting on a third 10 kilogram object located 50 meters to the right of the second asteroid, and C, the point between the two asteroids where F net equals 0. So this case, we have 3 objects. We have the 2 asteroids plus the third object that is 10 kilograms. So I'm going to be very creative in naming them, and I'm going to call the first asteroid mass A. The second asteroid is mass B, and mass C for our smaller object, which is 10 kilograms. The 2 asteroids are separated by 100 meters. And in part A, MC is 50 meters to the left. Part B, MC is 50 meters to the right. And in part C, we're actually trying to find a neutral point between them. So we're looking for the point between the 2 asteroids where F net is equal to 0. So where we would actually be able to place our third mass so the net force is equal to 0. And that one involves some more tricky algebra. So for part A, we're looking for F net acting on object C. Part B, also looking for F net acting on our third object. And part C, we're trying to find position where F net equals 0 newtons. So we're going to be using Newton's universal gravity. And in this case, I'm using the M1, M2 notation because all the objects are closer in size than, say, for example, previous questions where it was planet versus satellite. So for part A, we're looking for the net force acting on C. First of all, let's start off with our system diagram. In our system diagram, MA and MB, the larger and the smaller asteroid, is separated by 100 meters. MC is located 50 meters to the left of MA, and they're all on a single line. So the next step is to draw the free body diagram acting on object C. So here's our MC, and let's color code these. Let's make MA blue, and MB will make green. So MC is feeling the force of MA towards the right, and is also feeling the force of attraction from MB as well, which will also be to the right. So we have the force of gravity of A on C and the force of gravity of B on C. Or to clean up that notation a little bit, as you can see, this is a bit of a third law thing going on here. Force of gravity between AC and force of gravity between BC. So let's find F net acting on C. Well, F net acting on C is equal to FGAC plus FGBC. Dropping the vector notation, FGAC is pulling to the right, and the formula is GMA-MC over RAC all squared. And for BC, also pointing to the right, making it positive. So that's GMB-MC over RBC all squared. To clean up the algebra a bit, I'm going to take a common factor of G and MC out. Now let's substitute our values in. So the mass of A is 5 times 10 to the 5. Now let's talk about the distance of RAC. So the distance between mass A and mass C is 50 meters. So that'll be 50 squared. We have to be careful of the second one. The mass is 1 times 10 to the 5. So the mass of B is 1 times 10 to the 5. But the distance between B and C is 50 plus 100, or 150 squared. And this works out to 1.364 times 10 to the negative 7 newtons. So in part B, we're looking for the net force acting on C, but the system diagram is different this time because MC is to the right by 50 meters. So the free body diagram of C in this case is also going to be a little bit different. So our first vector is the force of gravity between B and C. Then our second vector is the force of gravity between A and C. If you notice, the forces this time are pointing to the left. So F net acting on C is the force of gravity of BC plus the force of gravity between AC. F net C is equal to negative, because it's going to the left, big G MB MC over RBC squared minus big G big M minus big G MA MC over RAC squared, taking a common factor of negative G in MC. So we've got negative GMC bracket MB over RBC squared plus MA over RAB squared. Note, it's very important. I make this mistake all the time still. When you take the common factor of the negative, that turns into a positive. And that's an easy mistake to make. Very common. So notice this time, RBC is 50 meters away and RAC is 150 meters away. Also, be careful of this notation down here, which gives us negative 4.150 times 10 to the negative 8 newtons. Part C, find a point between A and B where F net is equal to 0. So let's draw the system diagram now. So now with this setup, MA and MB, the two asteroids, are still located 100 meters apart. Next question is, where do we place our third object, MC, so that F net is equal to 0? And for that to occur, the force from A must be balanced out from the force of B. So let's consider this. All right, so let's take our MC. Now, our MC has to be placed somewhere in the vicinity. Now, if we place our MC right here in the middle, is that going to work? Well, according to Newton's universal gravitational law, the larger mass is going to have more of a gravitational pull than the smaller mass will at equal distances. So if we place MC right in the middle, MA is still going to have a stronger pull because it is 5 times more massive than MB. The other factor is proximity. The closer we are, the stronger the force of gravity. The further we are, the weaker it is. So we want to effectively weaken A's influence at the same time strengthen B's. So to do that, we have to migrate this over closer to B. Now, by doing that, we have to be careful because if we get too close to B, but then B becomes too dominant. So there's a sweet spot. So the question is, where is this located? Well, we know that position, this position here, is somewhere within this 100 meter limit. So for the sake of argument, let's say that the distance from position A to C, let's call that distance X. And from C to B, that's going to be 100 minus X. Now, notice these are just distances. All right, so next step, what we're going to do is we're going to set up our free body diagram. So MC is feeling a pull to the left from MA. At the same time, MC is pulling an equal force to the right from MB. So this is the force of gravity of between A and C, and this is the force of gravity between B and C, and they have to be equal and opposite to each other. So let's analyze the net force acting on C. F net acting on C is equal to the force of gravity between AC plus the force of gravity between BC. The key to this is the net force at this position is equal to 0. FGAC is pulling to the left, making it negative. FGBC to the right. Bringing this term, the negative term, to the left-hand side, we get the magnitude of the gravity between AC and the magnitude of the gravity between BC equal to each other. Using Newton's universal gravitational equation, G MA MC over RAC squared is equal to big G MB MC or RBC squared. Now, a couple of convenient things happen. Big G cancels out. This is on both sides of the equation. Also, our MCs cancel out. So we got significant reduction in the complexity of our equation. Next up, we're going to continue doing this algebraically. Well, as algebraically as we can. I'm not going to substitute in for MA and MB yet, but I am going to replace RAC and RBC. So RAC is just X and RBC is 100 minus X. There are a couple of ways to go about this question now. We actually have to solve for X, and the ugly way to do this question is to expand this using binomial expansion, or some of you know it as FOIL, and then cross multiply, and we end up getting a pretty ugly quadratic, which means we'd have to use the quadratic formula. However, there is a really, really simple way to do this problem, or shall I say, simpler way to do this problem. And we have an advantage. And we can only do this because of this case. On the left-hand side, we have a single term. On the right-hand side, we have a single term. Don't get confused by this. That's inside a bracket. I know those are two terms, but those are inside a bracket for now. The square is the offending issue. Well, what we can do is we can actually take the square root of everything, both the left side and the right side. So we can take the square root of the left side and take the square root of the right side. Well, what that does is it makes the numerator the square root of MA, but the square root of X squared is just X. Technically plus or minus. We're just going to go with the plus. The square root of MB is the square root of MB, and the square root of bracket 100 minus X is just 100 minus X. This simplifies the problem significantly because now we no longer have a quadratic. Now we still have to do some algebra because we have our X terms, our X factors, I should say, and they are located currently in the denominator. So we have to, first of all, get rid of our fractions. Well, how am I going to do that? I'm going to cross multiply. So I end up getting the square root of MA bracket 100 minus X is equal to X times the square root of MB. And then what I'm going to use is I'm going to use distributive property. So when I use distributive property, I'm going to take MA here and I'm going to distribute across the two terms inside the bracket. So I get 100 square root MA minus X square root MA is equal to X square root MB. So now I have three terms in total. The terms of concern are these two terms here. So I need to collect like terms, which means I got to bring this X term over to the other side. Now, the reason why I'm bringing this term here to the other side is because of this negative here. So this gives us 100 square root MA is equal to X square root MB plus X square root MA. As you can see, X is common to both of these terms. So I'm going to take a common factor. And finally, I'm going to isolate for X. Well, this bracket is bonded via multiplication. So that is multiplication inside there. The opposite of multiplication is division. So we're left with 100 root MA over root MA plus root MB equals X. Now, I switched the order of these things for no other good reason other than I prefer them to be in alphabetical order, which I realize is a very particular thing and not necessary. It just looks prettier in my opinion. All right, so now we simply substitute the values in. At this point, you could substitute the values straight into your calculator and get the answer. But I do want to show you another simplification. And this is kind of important, and especially if you're ever in a course post-secondary where they're expecting you to do things more algebraically and less reliant on your computer. I want to talk about this. This is multiply. It's a multiply sign, which of course gets confusing with the letter X. So we have to look at it through context. Well, I'm going to show you something. You can actually take these factors and separate the square root. Let me give you an example. Let's say we had square root of 4 times 9. All right. So square root of 4 times 9 is the same as the square root of 36, which is equal to 6. My argument is we could actually break this apart as the square root of 4 times the square root of 9. We can actually break up the product here into 2 separate roots. So this gives me 2 times 3, which is equal to 6. So the reason why I want to do this is there's actually a simplification that we get by doing that. So that's 100. And that's going to be root 5, root 10 to the 5. Root 5, root 10 to the 5, plus root 1, root 10 to the 5. Now, if you take a look, every term has a root 10 to the 5 in it. Since every term in the numerator and the denominator has that, we can cancel those out. So we're left with something a little easier to calculate. And it just makes a easier calculation. Again, optional. So the final answer is 69.10 meters, which makes sense because it should be closer to MB. So X is the larger of the two numbers, and that's what we're expecting. So there you have it. Much simpler than it initially looked.